Welcome back. In this segment, we'll be studying Chapter 6, which is the normal distribution. If you've ever taken a psychology class or a sociology class, you may have seen the graph of what's called the bell curve in your textbooks. The normal distribution is the most commonly used distribution in all of statistics. It's also the most abused distribution. I often have fellow professors ask me, should I put my grades on a normal curve? And I answered, that depends. What does the distribution look like when you plot your data? So before we can say that something follows the normal distribution, what we need to do is see, what does the data look like? Well, several of my students did that for a project a few years back. They did a survey and they asked other students, how fast do you drive on the freeway? And then they collected the data on how fast they drove on the freeway, and they made a graph of this data in their histogram. Now, when they first showed me the data, it looked like this. Here we have a graph of the data up here, and we can see, maybe soon, we can see that the data is listed as one person said, no, I don't drive on the freeway at all. Well, that one we don't want to put down as 0 because it's not a 0 speed. And then 3 people said I drive at 55, 5 people said 60, and so on. Well, looking at the frequency column is a bit tedious, and especially if we had a much longer column, it would be very difficult to see a pattern. So as we learned in Chapter 2, what we do is we draw a graph. And here we have a graph of the freeway speed. Now, if you notice, I'm starting down here, going from 55 to 60, 65, 70, and so on. I'm not starting at 0, and I didn't include the person who said, I don't drive on the freeway. If we look at this graph and we start to connect the midpoints of the tops of the bars, we can see that just based on this survey, which, by the way, was just a survey of 40 people, which is not a large sample, of course, we can see that we're starting to get a graph that looks a little bit like what's called the bell curve. In fact, another group of students in a different class, in a different year, did the same survey, where they surveyed 200 students, or 200 people actually, and they asked them, how fast do you drive on the freeway? They got almost an identical bell curve, except that it filled in much closer and was even more fitting of the theoretical distribution. Now remember, even though we're rounding the data to the nearest mile per hour or 5 miles per hour that somebody's driving, this is still continuous data. The normal distribution is used in almost every discipline that we have. Psychology IQ scores tend to be normally distributed, centered around 100. Body temperature of adults tends to follow a normal distribution. The height of adults tends to follow a normal distribution. The parameters that we're interested in when we study the normal distribution are the parameters of the mean. So this is the population mean we're interested in. And the population standard deviation. So we're interested in the population mean and the population standard deviation. Now, the actual graph of the normal distribution has a density curve that's very difficult to arithmetically or with calculus to solve. And I want to just show you the graph right here. Here's the graph of the normal distribution. And if we look at this shape right here is what I'm looking at. The function to graph this, f of x, is in your textbook and is a very complicated function. One, in fact, that usually when somebody is taught to estimate how to integrate that function, it's only based on using numerical approximations. Now, recently I was overseas and I was in Germany, and on the German mark, the 10 mark note, they have a picture of the normal distribution, and I want to just show you this right here. Here we have the normal distribution, And I don't know if you can see too much of this right here, but this is Carl Gauss. He is a very famous, or he was, not quite alive anymore. Maybe you could tell by the outfit. It's from the olden days. A very famous mathematician. And he is the one who quantified and wrote the density curve for the normal distribution. Now, on this 10-mark note, what we have is the bell curve right under here, and right next to it in the tiniest, tiniest font, and I'm going to zoom right in here so you can see this. Okay, what you can maybe see now is that there is a formula back here. Even if you can't read it, it's in the text, but it shows here's the bell curve, and it's attributed, and this is the formula for it. Hopefully what you can see is that it's long. It's a long formula. And so what we don't do is we don't spend time integrating this. You would not be able to do calculations. And in fact, up until the past 5 years or so, textbooks have and students have only been able to find probabilities using a chart that's been summarized and put in the back of every statistics book I have ever seen called the normal distribution chart. These probabilities were there. Now, thanks to the technology of personal computers and graphing calculators, we're able to do this by ourselves by holding the graphing calculator. All right, so now what we're going to do is talk about the uses of the normal distribution. The notation that we need to have for the normal distribution is we say x follows the normal distribution centered at whatever mean we have and whatever standard deviation we have. So here we're representing the average, and over here we have the standard deviation. Now I want to point out that there are actually two sets of notations that are used for the normal distribution. This is the first one. The other set of notation that's commonly used is the mean, and then what goes in here is the variance. And so whenever you see the normal distribution, what you need to do, your responsibility as a consumer of statistics, is to find out which format the normal distribution is being used in. And I see it goes through trends. Many years back, when I was a student, it was just sort of the tail end of the normal distribution being put into this format. And for 20 years or so, I saw this as the most common. Now I'm seeing a trend back to putting in the average and the standard deviation. And so you have to just check whatever study that you're doing and see which way the distribution is being represented and which format we use. All right, once we know these two, we know everything that we need to know in order to find areas and to find probabilities. And I'm going to go back to the example that I had over here before, the graph that we had right here. And on this part, we have our graph, and it's centered at the mean. By the way, hopefully you see that this is a symmetric distribution with half the area on the left and half the area on the right. We have a symmetric distribution, so that the mean is actually the 50th percentile, or the median in this. Now let's think about what would happen to the data if we took each data value and we added 5 to each data value. So let's say you were taking a class with an instructor, and the instructor said, oh, I feel so badly about these low test scores, I'm going to add 5 points to everybody's test score. Now, I'm never going to do that, so you don't have to worry about that happening. But let's say there was an instructor who was doing this. And then the person who had the median test score will have 5 points higher, as will the person who had the top test score, as with the person who had the bottom test score. So what's going to happen in this case is that the distribution would stay the same, but every value would have 5 points higher. So x would then follow the normal distribution. The new mean would be the old mean plus 5, and we know that because each value would have 5 more. But the spread of data would be the same. So for example, if the standard deviation was 10 before, it would still be 10. All that would happen is that instead of being centered at 5, at mu, we would be centered at mu plus 5. And our graph would look just like the other one, but pushed over more, pushed over 5 units. Every value would just be 5 units higher, and the distribution would still look the same, just shifted over. All right, what if we multiplied each data value by 3? Well, then a score of 5 would become 15, but a score of 100 would move over and become 300. So in this case, the data is going to be spreading out, and we still have to have, remember, the area under the curve is 1. The area under this curve is 1. Now, let's say we had a center of mu before. The new mean is going to be 3 times the old mean, and the data will still start at 3 times whatever the lowest value is, but go up to 3 times the highest value. So if we're spreading out here, let's look and see what's happening. The spread is getting much bigger, and the height is getting lower. So when we multiply each value by a number, the mean changes, and does the standard deviation. How about if we multiply by a number less than 1? In this case, 1/4. Well, now the mean will become 1/4 of the original mean. Each data value will be 1/4 of the original data value. And now the lowest will be 1/4 of the lowest, but the highest will move in. And we'll still have to have, we'll be spreading less. Our standard deviation will go down, but the area under the curve will still be needing to equal 1. So if the area is equal to 1, then we're going to have to go higher. And so our standard deviation becomes smaller, and the graph becomes higher, because the area still is equal to 1. Well, I'm going to do an example with you now. This is an example of data from a student of mine in the past, Terry Vogel. She was a student of mine in both elementary statistics and in calculus. And Terry is, or I'm not sure if she still is, but at least she was at the time, an amateur motorcycle racer. And she shared with me her logbook, which showed how fast she did her laps. She had 2.5-mile laps in a 7-lap race. And we graphed her data and found that the data followed almost a perfect bell curve. It was absolutely amazing when we did this. And she had an average of 129.71 seconds per 2.5-mile lap with a standard deviation of 2.28 seconds. The distribution was bell-shaped, and I didn't just make that up. It was from actually doing the graphing and testing it to see if it was. And we're interested in one of her randomly selected races. Her logbook, by the way, a segment of her logbook, happens to be printed as one of the data sets in the textbook. In words, define the random variable. So x, what we're measuring, it's continuous data, is the time to complete one lap. The distribution is normally distributed. The mean is 129.71, and the standard deviation is 2.28. Now we want to find the percentage of her laps that are completed in under 130 seconds. Okay, so we have the center at 129.71. We label this x. This is our number line. X, our random variable, what we're measuring. And what we're finding is the probability that x is less than 130. That's what we're looking for. The probability that x is less than 130. Well, 129.71 is here, so 130 must be to the right of the mean. I don't know where. I don't know if it's close by here or if it's out here. Actually, I do have an idea based on the standard deviation. I think it's probably pretty close. Here's 130. Less than 130, so I'll be shading in this way. So We're going to find this on a calculator or through a calculator program or through a computer software program, but I'm going to go on calculator to find it. And on this one, I'll have go into distributions. And now you see that the top three distributions deal with the normal distribution. The very top one, the PDF, gives a value on the curve. So even though when we were studying the discrete distributions, we found PDF, which was a value of x, for the normal, we're actually getting a value on the curve. So we don't want to ever use that one. The CDF, cumulative area, gives area between two values. And the inverse normal is for when we start and we want to find the percentiles. So I'm going to do the second one here. The notation for this calculator, anyways, is to go from the lower limit, which would be 0. That's the fastest that she could ever finish a race in, which, by the way, doesn't make sense. You can't actually have 0, but we know that this is the interval, to 130. And the mean was 129.71, and the standard deviation is 2.28. And of course, you're aware of the fact that whatever technology you're using, you're going to need to know the notation for that technology. I know the ones for the TI calculators. And we find that this area is 0.5506. So the area here is 0.5506, which is the probability that x will be less than 130. What if we wanted to find the probability that she finishes between 120 and 130? That one's not down here, but let's just do that one anyways. The probability that she finishes between 120 and 130. Now I'm going to go from 120 to 130. The mean and we have, oops, what did I do? Oh, it's still 0.5506. Now, let's think about that. 120 to 130 is the same as 0 to 130. Well, first off, they're not the same. It's that I have my calculator set to round to 4 decimal places. If we went out enough decimal places, we would find that they're not the same. But what this tells me is that on this graph, 120 is way down here. And if we think about it, a standard deviation is 2.28 in this case. 120 is almost 4 standard deviations below the average. Okay, let's see if you can think about that part. 2.28 is 1 standard deviation. So if we subtract a standard deviation once from 129.71, we get right about here. If we subtract it again, here, here. So we're way down here. So what this is telling us by having the area almost the same is that the area under the curve here between 0 and 120 is so small that to 4 decimal places it's insignificant. Now let's look at the next one. The fastest 3% of her races are under, now we're looking for a time. We're not looking for a probability. We have the probability, 3%. So we're looking for, here's 129.71. Here's x. And this area is 0.03. So now we're looking for the value so that the probability that x is less than k equals 0.03. We're looking for the k now. So we're looking for what value will give us an area to the left of it of 0.03. All right, let's try this one now. On this calculator, we go into the inverse normal, and we put in the percentile that we want, 0.03. And then we put in comma, and then the mean, and the standard deviation. So what I'm looking for now is I want 3% in the tail. And I find that that's 125.4218. So what that tells me is that 125.4218 125.42, that the area to the left of 125.42 is equal to 0.03. All right, we're going to do one more. The middle 80% of her races are from what to what? In this case now, we go to draw the graph, the middle 80%. Okay, so we're looking for the middle 80% of her races. Okay, I want the area in the middle to be 0.8, 80%, the middle part. Well, I know that I'm centered at 129.71. I'm labeling this X. I need to find this value and this value right here, A and B. Now, if I'm looking for the middle 80%, that means I have 20% left over. And if the 80% is in the middle, the 20% should be split evenly on the left side and evenly on the right side, meaning I should have 0.10 here, 10% of the area here, and 0.10% of the area here. And so if we want to find the area to the left for A, we're going to go in here, and we're just going to change that 3% to a 10%. And we find that we have 126.7881. But now, for the B, we're not going to look up 80%. It's 80% plus this other 10%. So 80% plus the other 10%, which would be then the 90th percentile. So for this last one, we're going to be looking up, for B, we would have 0.90, 10% plus 80%. And we will then change this 10% to a 90 percentile. And we have 132.63. So that tells us that our middle 80% go from 126.7881 up to 132.6319. All right, we have one last part to do over here, and the one last part that we have to do now is just talking about one type of normal distribution called the standard normal distribution. And I just want to discuss that one last. The standard normal distribution is a special distribution, a special normal distribution denoted by capital letter Z. And this is reserved for the standard normal. And the standard normal is a distribution that is centered at 0 with a standard deviation of 1, which means that the variance is also 1. It's a very specific case. And how we standardize a value is we take our value, subtract out the mean, divide by the standard deviation, and what's left is what's called the Z value, or the Z-score. And what this represents, Z is equal to how many standard deviations a value is from the mean. So, for example, let's look at this case. In this case, let's say we wanted to find the Z-score. Well, this will be the last thing that we'll do, actually. Find the Z-score, or find out the Z-score, that's sort of what we nickname it, for 135 seconds. Okay, so we have Z is equal to 135 minus 129.71 over 2.28. And that will tell us how many standard deviations the number 135 is from the average. And we get 2.32. So what this 2.32 says is that the number 135 is 2.32 standard deviations above the average. If we ended up with a negative z-score, that would tell us that our number is below the average. Well, that was the normal distribution, and there are many applications for this and many problems, and the best thing for you to do is just work through these. And in the next segment, Chapter 7, we're going to be studying one particular aspect and use of the normal distribution. Bye-bye.